Imagine for a moment your most sensitive data financial records, private health information, maybe even national security secrets. It's all nestled safely, you believe, behind an advanced encryption algorithm, one that is, mathematically speaking, absolutely unbreakable. But now, picture this. A simple probe, just inches away, silently picking up faint, almost imperceptible whispers of information emanating from the hardware processing that data. Enough whiskers, in fact, to completely crack that supposedly ironclad encryption. That, my friend, is the unsettling and very real reality of side-channel attacks. Welcome to the Deep Dive. Today we're plunging into a world where cutting-edge cryptography collides head-on with the sneaky physical vulnerabilities inherent in hardware. We're going to unravel the intricacies of how even those mathematically secure algorithms can leak vital clues, and then we'll uncover a groundbreaking new defense system, one that's transforming the landscape of digital security called Syn-STELLAR. Our journey today is guided by a remarkable and very recent paper from a brilliant team at Purdue University and Intel Labs titled Syn-STELLAR, an empower-scale resilient AES-256 with synthesis-friendly signature attenuation. This paper details how researchers have managed to significantly boost the security of the ubiquitous AES-256 encryption engine against the very real and growing threat of power and electromagnetic side-channel attacks. What they've achieved pushes protection levels to truly unprecedented heights, promising a future where our digital defenses are far more robust. Our mission in this deep dive is to delve into the cutting-edge details of these complex attacks and their ingenious new defenses. We want you to understand not just what they are, but why they critically matter, how they operate at a fundamental level, and what makes Syn-STELLAR such a significant, even revolutionary leap forward in hardware security. We'll break down the core concepts, explore the exceptionally clever circuit designs, and analyze the impressive real-world results, ensuring you leave feeling thoroughly informed and perhaps a little surprised by the sheer ingenuity involved in this hidden arms race.
It's truly a fascinating area because on paper, many cryptographic algorithms like AES-256 are considered impenetrable. They rely on mathematical complexity that would, in theory, take a supercomputer billions of years to brute force. It's just mind-bogglingly complex. But as you said, the moment these algorithms are instantiated in physical hardware, say a chip in your phone, a secure smart card, or a server in a data center, that physical implementation introduces an entirely different dimension of vulnerability. It's a layer of attack vector that many people, even those deeply involved in cybersecurity, don't often consider. It's kind of hidden in plain sight.
Okay, let's unpack this. We're talking about side-channel attacks. For those of us who grew up thinking encryption was purely a digital mathematical game, what exactly are these and why do they pose such a distinct threat?
Precisely. That's the crucial distinction, and it's a paradigm shift in how we think about security, really. What are side-channel attacks? Well, it's about going beyond mathematics. Cryptographic algorithms are indeed mathematically robust, designed with incredible theoretical strength. But when these algorithms are implemented in physical hardware, and that could be anything from a tiny microcontroller in an IoT device to a high-performance processor, that hardware isn't perfect. It's a physical entity. As it computes, it leaks information. These leaks aren't the sensitive data itself, like your password, but rather physical manifestations of the operations being performed. Think of it as ambient noise that inadvertently reveals secrets, little clues given off by the machine doing its work.
So if I'm understanding correctly, it's like eavesdropping on the physical effects of the computation, the electrical hum, maybe the heat signature, the timing of operations, rather than trying to directly break the math of the code.
That's right. You've hit on it perfectly. And these physical manifestations can take several forms. While we'll focus today primarily on power consumption and electromagnetic emissions, which are the main targets for Syn-STELLAR, it's worth noting there are other types of leaks. For instance, timing attacks exploit variations in the time it takes for an operation to complete, which can reveal secret-dependent execution paths. Cache attacks monitor patterns of cache hits and misses in a processor, similarly betraying secrets. It gets quite subtle. But for this deep dive, our lens will be on correlational power analysis, or CPA, and correlational electromagnetic attacks, or CEMA. These are the most prevalent and powerful physical attacks against crypto hardware, and the ones Syn-STELLAR is specifically designed to counter.
That brings us to the threat and its impact. How serious can these leaks really be? Because I'm still trying to wrap my head around how a tiny bit of power fluctuation could compromise something as supposedly strong as AES-256.
Here's where it gets really interesting and frankly quite alarming in its practical implications. The impact is profound because side-channel attacks can drastically, almost magically, reduce the computational effort required to break even the strongest encryption. The research paper highlights a truly staggering example that puts this into stark perspective. the time complexity of breaking the AES-256 encryption engine, which normally requires an astronomical 2256 operations. That's a number so large it's essentially unbreakable by any imaginable computer for the foreseeable future, can be reduced. Get this, down to a mere 213 operations.
Wait, 2 to the power of 13, that's what, 8,192 operations, is that
Yeah.
right? That's not just a reduction, that's a total demolition of the cryptographic strength. What does that practically mean for the real-world security of systems relying on AES-256 today?
That's precisely the point, 8,192. It transforms an utterly impossible task into something that could be done in seconds, maybe minutes, with common computing power, even a basic laptop. For industries like finance, where billions of transactions happen daily, or for healthcare systems protecting sensitive patient data, or even for national defense, where secure communications are paramount, such a reduction in security isn't just a vulnerability, it's a catastrophic failure waiting to happen. It means that the theoretical mathematical strength of the algorithm is rendered almost moot by its physical implementation. The physical world betrays the math. And this isn't just an academic exercise confined to specialized labs. There is a very concerning real-world vulnerability here. The research points out that AES-256 keys can actually be sniffed from up to a meter away using a relatively cheap electromagnetic probe, like off-the-shelf cheap. What's even more concerning, and what truly highlights the practical danger, is that this can be done without needing any detailed knowledge of the circuit design, the silicon layout, or even the PCB implementation. This underscores that an attacker doesn't need to be a hardware design expert or have direct physical contact with the device to potentially extract your deepest secrets.
A meter away. With cheap gear, no inside knowledge needed. Wow. Okay, that really brings the threat home. So we've established the threat is real and potent. But how do these correlational attacks actually work? It sounds almost like magic, but there must be a methodical process to extract such sensitive information from what seems like mere noise.
There is indeed, and the methodology is quite ingenious in its simplicity and effectiveness. It starts with trace collection. Attackers use sophisticated equipment, like high-speed oscilloscopes, to collect traces. These traces are essentially very precise recordings of the power consumption fluctuations or electromagnetic emissions from a device as it performs encryption operations. They're looking for any subtle patterns, no matter how faint. Think of it like recording the sound the chip makes while it's working. Crucially, in many real-world scenarios, the corresponding output ciphertexts for each encryption are often publicly available. Think about a smart card processing a transaction. The encrypted output might be visible on a public network even if the secret key itself is not. The attacker often has the input and the output, just not the key. The next step is guessing and modeling. Now, attackers don't try to guess the entire 256-bit key at once. That would still be way too hard. Instead, they attack small portions of the secret key, typically 1 byte at a time, just 8 bits. For each possible guess of that 1 key byte, and there are 256 possibilities for a single byte, they build a Hamming distance HD model.
Hamming distance. Okay, can you break that down a bit?
Sure. Hamming distance, it's essentially how many bits flip or change during a specific operation with the encryption algorithm, like going from 0 to 1 or 1 to 0. The critical insight for attackers is that these very bit flips, and thus the Hamming distance, directly translate into subtle, measurable variations in power consumption or EM emissions. More flips, generally more power, or a slightly different EM signature. So by predicting the HD for each key guess, they're essentially predicting the power or EM signature the chip should emit if that particular key byte guess were correct.
I see. So they make a guess for a tiny piece of the key, predict the energy fingerprint that guess should cause, and then they compare that prediction to what they actually recorded.
Exactly. That's the core of the attack. Correlation. They correlate these predicted HD values with the actual traces they collected from the device. They're looking for a statistical match. It's like finding a distinct hidden pattern in a sea of seemingly random noise. Which guess consistently matches the real-world measurements? If a particular key byte guess consistently shows a very high statistical correlation with the collected traces across many encryption operations, it's a strong statistical indicator that this guess is correct. After analyzing multiple traces, sometimes thousands, sometimes millions, depending on the noise and the countermeasure level, the correct key byte can be recovered through this correlational analysis. They then repeat this process for the next byte and the next, and before you know it, the entire 256-bit secret key is exposed, completely bypassing all the mathematical complexity of AES. It truly is a testament to the power of physical observation, finding signal in noise.
That's incredibly clever in its execution and genuinely terrifying in its implications. So, knowing this threat exists, there must have been an intense arms race to develop defenses. What were some of the early attempts to combat these side-channel attacks, and what were their inherent limitations?
Indeed, it's a relentless cat-and-mouse game between attackers and defenders. And yeah, the side-channel countermeasure community has made significant progress over the years. It's evolved from early logic-level and architectural countermeasures to more robust and ultimately more generic circuit-level solutions. The first two categories, logic-level and architectural, are generally considered design-specific. That means they are tightly coupled to the encryption algorithm's implementation, tailored. At the logic level, techniques revolve around the fundamental principle of power balancing. The core idea here is to make the instantaneous power consumption of different operations as uniform as possible. Basically, try to make a DRAM operation consume the same power as a one operation. If you can do that, you mask those key-dependent variations an attacker could exploit. Examples include sense amplifier-based logic, SABL, dual-rail pre-charge circuit, DRPC, and wave dynamic differential logic, WDDL. Fancy names, right?
Definitely sound complex.
Well, SABL and DRPC aimed to equalize gate-level power consumption, but they required specific custom library cells, special building blocks. This translates into a considerable amount of manual engineering effort, really painstaking work for designers. This makes them notoriously hard to implement broadly across different designs or to port to new manufacturing processes, becoming a significant bottleneck in chip design. WDDL, on the other hand, was pioneering because it could be designed using standard cells, which is a big advantage for automation. But its drawback was substantial. It suffered from very high power consumption, a large area footprint on the silicon, and often performance overheads. Limits its practical use, especially for, battery-powered devices.
So these early methods worked, but they were either too bespoke and labor-intensive to be practical, or just too inefficient for mass adoption, like too power-hungry or bulky.
That's a perfect summary. Then you have architectural countermeasures. These methods attempted to distort the side channel trace itself by injecting noise. For example, inserting dummy operations that do nothing useful but consume power, hoping to confuse the attacker, or shuffling the order of operations to make correlations harder, or using more complex arithmetic countermeasures within the algorithm itself. They are effective to a degree, but their main limitation is that they are intrinsically constrained by the specific architecture and algorithm being protected.
Ah, so they aren't generic fixes.
Right. There's only a finite number of operations you can shuffle or dummy tasks you can insert before performance is unacceptably impacted or the technique runs out of steam. This makes them non-generic and less scalable, especially when aiming for the highest security levels, as they are intrinsically tied to the particular cryptographic engine rather than offering a universal shield. You have to redesign them for every different chip or algorithm.
It sounds like those earlier methods were a bit like putting a very specific hand-tailored Band-Aid on a problem that needed a more systemic solution. What about more fundamental circuit-level countermeasures? These sound like they're getting closer to the hardware's core.
This is indeed where things get more physically robust and potentially more generic in nature. These approaches are designed to be more broadly applicable. They aim to act as a wrapper or protective layer around the encryption engine itself, rather than requiring specific changes to the algorithm or its date-level implementation, kind of like putting the whole engine inside a shielded box. The first generation of these circuit-level countermeasures included techniques like current equalizers, series low dropout, LDO regulators, and integrated voltage regulators, IVRs. These techniques were able to enhance protection up to about 10 million minimum traces to disclosure, or MTD.
Minimum traces to disclosure. Okay, MTD. That's a crucial metric here, isn't it? For those unfamiliar, what exactly does MTD mean in practical terms, and why is 10 million traces still not good enough?
MTD is absolutely critical for quantifying security, yeah. It tells us how many traces, those power or EM recordings, an attacker needs to collect to successfully extract the secret key. Basically, how much effort they need to put in. So 10 million traces might sound like a lot to an ordinary person. 10 million measurements. However, for a determined attacker with modern, readily available lab equipment, collecting billions of traces rapidly is entirely feasible, sometimes within hours or even minutes. Therefore, 10 MMTD, while an improvement over zero protection, is still considered quite vulnerable in the face of sophisticated, high-volume attacks. It's a significant milestone, but not the finish line, not for high-security applications anyway. Furthermore, these early circuit-level solutions had their own inherent set of challenges. IVRs, for instance, often suffered from a reliance on high passive components like large onboard inductors or capacitors. This makes them costly, bulky, and sometimes inherently vulnerable to other forms of physical tampering. Series LDOs could also be insecure if the instantaneous current drawn by the LDO circuit happened to precisely equal the AES current, inadvertently creating a new exploitable leakage point, sort of defeating the purpose. Noise injection was also explored to reduce the signal-to-noise ratio, which helps improve security.
Making it harder to find the signal.
Exactly. But it came with a very high power overhead, making it impractical for many applications, especially in battery-powered or low-power IoT devices where every bit of energy counts.
So still not good enough. And introducing new trade-offs, it really is an arms race.
Yeah.
What came next in this relentless quest for better security?
The next major evolutionary step involved switched capacitor-based current equalizers, such as the pioneering work by Tokunaga and his team you might have heard about. This technique achieved a significantly higher MTD by cleverly isolating the encryption engine from the main power supply, VDD, for brief periods and periodically connecting it to an AC ground. This effectively bypassed or shunted key-dependent leakage currents away from the observable power rail, leading to much better security than previous methods. A smart idea. However, it still had significant drawbacks. It often suffered from noticeable performance degradation because of the intermittent power supply, kind of like starving the engine temporarily. And crucially, it wasn't easily scalable across different technology nodes. This was primarily due to its reliance on precise DC bias voltages and analog comparators, which require considerable manual tuning and recalibration for each new manufacturing process, again making it a high-effort, less flexible solution. Analog stuff is often tricky to scale.
So a good idea, a step forward in security, but still too analog and difficult to adapt to the rapid pace of chip manufacturing advancements.
Exactly. Then came a significant breakthrough with current domain signature attenuation, CDSA. This was the first truly single strategy solution that managed to achieve an MTD of over 1 billion traces, a massive leap forward that redefined what was possible. We're talking orders of magnitude better. CDSA worked by using cascode current sources, a type of analog current control circuit known for high stability and attenuation, for signature attenuation. This essentially made the current consumption of the AES engine appear much flatter and more constant to an external observer. Really smoothed things out. It also incorporated PMOS-based bleed paths to actively divert key-dependent leakage. However, its main challenge was still its heavy reliance on analog components, things like voltage stacks and analog comparators, which again meant considerable manual effort was needed for scaling across different technology nodes. This made it difficult to integrate into the predominantly digital chip design flows of today. Back to the same scaling problem. Finally, we also saw cascaded solutions that achieved comparable security levels. These combined approaches, like maybe randomized digital LDOs with arithmetic countermeasures, could also reach high MTDs.
Stacking different defenses together.
Right. The issue here was that each individual countermeasure alone only provided medium security, maybe around that 10 million MTD mark we talked about.
Right.
And the combined solution often came with a high power overhead and was still algorithm specific. This meant it wasn't a truly generic defense for any crypto engine, rather one specifically tailored to certain algorithms. You couldn't just drop it onto any chip. So while significant progress was being made, the quest for a truly scalable, digital-friendly, high-security, and generic solution that could easily integrate into modern chip design flows remained the holy grail. That's what everyone was searching for.
You've painted a clear picture of a progression from design-specific fixes to more generic circuit-level attempts, each with its own trade-offs, particularly regarding scalability and the reliance on complex analog components. This truly sets the stage for Syn-STELLAR, doesn't it? What's the core innovation here that allows it to overcome these historical hurdles?
Yes. This is where Syn-STELLAR truly shines, and it's a testament to incredible engineering that builds on decades of prior research, learning from all those previous attempts. The core innovation of Syn-STELLAR, which stands for Synthesis-Friendly Signature Attenuation Embedded Crypto with Low-Level Metal Routing. Quite a mouthful.
Yeah. Syn-STELLAR's easier.
Right. The core innovation is fundamentally about bridging the analog-digital divide. It ingeniously takes the best aspects of those powerful, strong analog protections we just discussed, concepts like signature attenuation and switched capacitor current equalization, and transforms them into an easily scalable, entirely digital-friendly solution. This is a monumental shift for chip designers. It makes implementing these advanced techniques much, much easier.
That sounds like a genuine game changer. Making something largely digital usually means it's inherently easier to design, test, reproduce, and adapt across different manufacturing processes compared to finicky analog circuits.
Absolutely, that's the huge benefit. The primary goal here was to achieve a significantly higher MTD than anything previously seen, but with an all-digital approach. This pushes the state of the art for a single, scalable countermeasure while crucially maintaining comparable area and power overheads to previous, less secure solutions. It's about achieving top-tier security without sacrificing the practicalities and efficiencies of modern chip design, making it a viable and attractive option for mass deployment. Getting the best of both worlds, really.
Okay, let's get into the nitty-gritty. You mentioned Syn-STELLAR takes the best of strong analog protections and makes them digital. What are the two fundamental circuit techniques, the two pillars of this Syn-STELLAR design that make it so effective?
Syn-STELLAR's is built upon two extremely powerful and complementary circuit techniques: the digital signature attenuation circuit, or DSAC, and the time-varying transfer function, or TVTF. Let's start by delving into the DSC. The digital signature attenuation circuit is founded on a key insight derived from previous research: that MTD, or minimum traces to disclosure, is directly proportional to the square of the attenuation factor.
The square. So double the attenuation gives 4 times the security in
Yeah.
terms of traces needed.
Exactly. This exponential relationship is what drives the design. Small improvements in attenuation lead to big gains in MTD. The primary aim of DSE is to make the instantaneous power consumption of the encryption engine as invisible or as constant as possible to the outside world, effectively flattening the signal an attacker would look for.
So it's trying to flatten out those telltale power spikes and dips that attackers look for,
Yeah.
making the chip's internal operations electrically silent from the outside, like putting a very good muffler on it.
Exactly right. A very good analogy. And it does this primarily with a digital-friendly current source, or CS. Traditionally, cascode current sources, which are complex analog circuits used to provide a very stable current, often seen in high-performance analog designs, offered great attenuation but were analog in nature. They required precise voltage biases and stable reference currents, making them notoriously hard to scale across different technology nodes and incompatible with automated digital design flows. The manual effort was significant. Syn-STELLAR replaces this with a stacked PMOS design. The stacked PMOS current source is fully synthesis-friendly. That means it can be designed using standard hardware description language, HDL, and automatically placed and routed by digital design tools. No handcrafting needed. It's also entirely digitally controlled. Its primary job is to supply the average crypto current to the AES engine, effectively making the current drawn from the main power supply largely independent of the instantaneous, rapidly varying current changes that occur during crypto operations. The research paper notes that this digital CS alone provides an impressive attenuation factor of about 41x.
Wow, 41 times just from that digital current source. That's a monumental step already. But what about those tiny delta changes in current that you mentioned earlier? Those residual key-dependent leakages that even an average current might not fully mask? How does DSA deal with those subtle remaining whispers?
Good question. That's where the truly ingenious innovation of the digitized bleed path with ring oscillators, ROs, comes in. Even with a highly attenuated average current supply, there will always be tiny key-dependent delta changes or quantization errors in current due to the inherent switching nature of digital circuits. It's never perfectly flat. These subtle changes, if left unchecked, are still enough to reveal leakage. A bleed path is therefore needed, a mechanism to divert this minute leakage current away from the main supply, effectively masking it from external observation. Syn-STELLAR uses a specialized ring oscillator as this bleed path. Now, an RO is usually just a simple circuit that oscillates, used for clocks or testing. But here, the RO is incredibly clever because it serves as a voltage-dependent current load. Think of it as a dynamic current sponge. When the AES node voltage, which we call VAEES, fluctuates, say, it increases slightly due to a key-dependent operation drawing a little less current than the average. The RO's oscillation frequency changes proportionally. As its frequency increases, the RO draws more current from the VAES node, effectively bypassing or bleeding off that excess key-dependent current to ground. This action keeps the VAES stable and, crucially, masks those critical, secret-revealing leakages.
So it reacts instantly to tiny voltage changes and cancels them out by adjusting how much current it draws itself.
Precisely. You can visualize it like a finely tuned, self-adjusting faucet that opens just enough to let out any excess water, keeping the water level in a basin perfectly stable, no matter the small variations in the incoming flow. This immediate localized current balancing act is called local negative feedback, or LNFB. It's constantly working to keep things smooth right at the source.
That's a very elegant solution. So the RO actively responds to voltage changes at the heart of the AES engine to maintain stability and prevent leaks. What other roles do these versatile ROs play in the Syn-STELLAR defense? You said they were versatile.
They are indeed incredibly versatile, performing multiple critical functions. They also function as global negative feedback, or GNFB. Beyond their local action, the RO's oscillation frequency provides a real-time heartbeat or measurement of the VAES voltage. It tells the system how healthy that voltage is. This frequency acts as an input to a larger digital control loop called the switched mode controller, or SMC. This SMC then intelligently adjusts the number of active current source slices, ensuring the VAES is kept precisely within a safe guard band at startup during heavy workloads or when environmental conditions change. Things like process variations during manufacturing, external voltage fluctuations, or temperature changes, often collectively referred to as PVT variations, keeps everything stable overall.
Okay, so local balancing and global stability control.
And there's more to their utility. The ROs also act as a powerful noise injector. Multiple ROs are strategically placed throughout the circuit. These can be randomly activated or deactivated, which in turn injects slight, randomized power supply noise at the VAES node. This intentional random noise further confuses attackers, making it much harder for them to discern any meaningful key-dependent patterns in the residual leakage. It adds chaff to the signal. So the RO really is a multi-purpose cornerstone component in this design, performing local and global stabilization as well as noise injection, a real workhorse.
It certainly sounds like the ring oscillator is doing a lot of the heavy lifting. How is all this sophisticated current regulation and noise injection coordinated across the entire DSEC?
That's handled by the Digital Current Source Controller Loop, or SMC, that I mentioned. This is a low-bandwidth asynchronous controller that continuously monitors the RO frequency, which, as we discussed, reflects the VAES voltage. If the VAES node voltage drifts outside a predefined guard band, which represents the safe and optimal operating voltage range for the AES engine, the SMC intervenes. It intelligently adjusts the digital current source slices, either turning some on or off, to bring the VAES back into the desired range. This ensures both stability and a high impedance for attenuation, crucially without leaking any data through the control loop itself. The controller itself has to be secure. The guard band is critical for both security and efficiency, ensuring the current sources remain their high impedance saturation region, which is where they perform their best attenuation, keeps them in the sweet spot.
Okay, that covers the digital signature attenuation circuit, the DSA. That's pillar one. Now, you mentioned a second pillar of Syn-STELLAR, the time-varying transfer function, or TVTF. What specific problem does this solve, and how does it contribute to the overall security?
Right, pillar two, the time-varying transfer function, TVTF. This is designed to address a fundamental limitation of even the most effective previous switched capacitor-based countermeasures. While those were good, remember they often suffered from analog resets and performance degradation issues. Syn-STELLAR's TVTF takes this concept into the digital domain with what we call digital time domain obfuscation. It's about messing with the timing of the leakage. The TVTF uses an array of 16 to 20 PF switched capacitors, summing up to a total capacitance of about 320 PF. Importantly, these are MOS capacitors, not metal insulator metal capacitors. That's a subtle point.
Why does that matter? MOS versus MEM.
Well, MEM capacitors are known to potentially radiate electromagnetic fields more strongly, possibly creating their own EM leak vulnerabilities, so using MOS caps avoids that potential issue. It's a critical design decision for robust security. These capacitors are continuously charged and discharged, but here's the truly clever part. The order in which they connect to the AES engine is randomly shuffled in the time domain.
Whoa, so it's not just smoothing the power, like the DSAC. It's actively scrambling the timing and path of the signals, making the leakage patterns completely unpredictable in time, like a shell game with the energy.
Precisely. That's a great way to put it. It effectively scrambles the side channel traces in a way that correlational attacks struggle to penetrate. Imagine trying to read a book where all the letters are randomly shuffled and rearranged every few seconds. It becomes incredibly difficult for an attacker to correlate specific current changes with specific encryption operations, because the channel through which that information might leak is constantly shifting. Each time an operation occurs, the energy signature appears in a different time slot and through a different capacitor path. This makes it almost impossible to statistically average out and find a consistent pattern related to the key. This sophisticated randomization is managed by a lightweight digital controller with internal memories and cascaded Fibonacci linear feedback shift registers, LFSR.
LFSRs. Those are common for generating pseudo-random sequences in digital circuits, right?
Exactly. They generate these pseudo-random sequences to control the complex capacitor switching order. For strong security, the seeds for these LFSRs are assumed to come from a true random number generator, TRNG, which are increasingly common in modern system-on-chips. TRNGs are critical for generating truly unpredictable randomness, so the shuffling sequence itself isn't predictable by an attacker. And there's also an optimal operation frequency for the TVTF that was carefully determined by the researchers through experimentation. The paper details a clever trade-off. TBTF operates at 6 times the AES engine's core frequency. This strikes a finely tuned balance, injecting sufficient noise and time domain obfuscation to port attacks without incurring excessive power overhead or causing significant voltage droop that would impact the AES engine's performance. You don't want the defense to kill the performance. So, by combining the DSA's powerful signature attenuation with the TVTS innovative time domain obfuscation, Syn-STELLAR achieves a truly formidable multi-layered level of security against both power and electromagnetic side-channel attacks. It's an elegant and comprehensive solution, hitting the problem from 2 different angles, amplitude and time.
This is an incredibly sophisticated and multi-layered design. It really sounds impressive on paper. But the proof, as they say, is truly in the pudding, or maybe in the silicon in this case. How did the researchers actually test Syn-STELLAR? And what were the real-world results they observed in their lab?
Exactly. This is where the theoretical elegance meets practical validation, and it's crucial. For the integrated architecture, the team implemented a parallel AES-256 encryption engine on a 65-nanometer CMOS test chip, standard but fairly modern process technology. This engine was designed for high throughput, capable of completing an encryption in just 14 cycles, which is quite efficient. Crucially, the chip was designed to be reconfigurable. This was a key part of the experiment. It allowed them to test 3 distinct modes. First, an unprotected AES-256 implementation, serving as a vital baseline you need to know how bad it is without protection. Second, AES-256 with only the digital signature attenuation circuit, or DSC, enabled. And third, AES-256 with both DSC and the time-varying transfer function, or TVTF, fully enabled. This represented the full Syn-STELLAR solution.
So they could isolate the effect of each part. DSC alone, and then DSC plus TVTF.
Precisely. This reconfigurable setup was brilliant because it allowed for direct and very clear comparisons of the security improvements provided by each countermeasure individually and then by their powerful combination. Made the results really unambiguous.
So they had a direct before and after comparison, along with that intermediate step, which is absolutely vital for proving the efficacy of complex security solutions like this. What are the actual measurement setup they use in the lab? How do they gather these crucial side-channel traces? Sounds like delicate work.
The measurement setup was, as you'd expect, quite sophisticated and meticulous, reflecting the high stakes of this research. You need good gear to measure these tiny effects. They used a top-tier 5 gigasamples per second oscilloscope to collect the extremely high-resolution traces that captures really fast changes. A powerful PC for processing the vast amounts of data generated, a DAQ, data acquisition card, for sending inputs to the chip, an arbitrary waveform generator for precise clock and enable signals, and standard DC power sources for the chip itself. A pretty standard but high-end hardware security lab setup. For probing the leaks, particularly the electromagnetic emissions, a 10mm H probe was used. The signals are tiny, so they amplified them by 40 degrees before feeding them into the oscilloscope for recording. Now, this specific choice of probe was very important and was a key part of their experimental design, not just an arbitrary choice. They performed a thorough analysis comparing it to much smaller, more localized probes, like a 100 micrometer Langer probe, which can pinpoint tiny areas. What they found was that the larger 10mm H probe actually yielded a 3x higher correlation coefficient with power traces compared to the smaller probe.
Wait, the bigger, less precise probe was better for the attack? That seems counterintuitive.
It does, but it makes sense when you think about it. It suggests that the useful leakage isn't necessarily coming from one tiny spot, but is more of a combined effect across a larger area. So the larger probe, while less localized, was actually more effective at capturing the overall EM signature needed for a correlational attack. This highlights the practical danger of less localized attacks, where an adversary doesn't need to know intimate details of the chip's layout, reinforcing the need for comprehensive protection. An attacker might actually benefit from a less precise measurement in some cases. The attack methodology itself was designed to be incredibly rigorous, simulating a highly capable and persistent attacker. Not just a casual attempt. They collected 1,000 average traces from a vast pool of 1.25 million unique traces.
Okay, averaging 1,000 traces. Why do that?
Averaging is a standard technique attackers use to reduce random noise in the measurements. By averaging many traces together, the random noise tends to cancel out, while the consistent, key-dependent signal gets stronger. So collecting 1.25 million unique traces and then averaging them down to 1,000 very clean traces simulates a determined and well-equipped correlational attack attempting to defeat robust countermeasures. It represents a strong adversary.
All right, this is truly the moment of truth. With such a sophisticated setup and rigorous testing, what were the results? You mentioned staggering earlier. What kind of numbers are we talking about here for the MTD, the minimum traces to disclosure? Did Syn-STELLAR live up to the hype?
The results were indeed nothing short of staggering, and this is where the aha moment really comes into play, demonstrating the monumental leap Syn-STELLAR represents. Let's break it down by mode. For the unprotected AES-256, our baseline, well, it was bad. Using correlational power analysis, CPA, the key was broken in a mere 7,000 traces in the time domain, just 7,000, and only 20,000 traces in the frequency domain. For correlational electromagnetic attacks, CEMA, the key was broken in just 9,000 traces in the time domain and 75,000 traces in the frequency domain.
So thousands of traces. That's almost instantaneous for an attacker with the right gear.
Absolutely trivial. These alarmingly low numbers unequivocally confirm just how vulnerable and unprotected AES-256 implementation truly is to modern side-channel attacks. It's wide open. Now, when they enabled DSE AES-256 as a single countermeasure, just pillar one, the improvement was absolutely dramatic. For CPA, it required an astounding 820 million traces in the time domain. 820 million.
From 7,000 to 820 million. Wow.
Exactly. And between 380 to 450 million traces in the frequency domain at 200 megahertz. This represents an incredible 25x improvement over the existing state-of-the-art for a single digital countermeasure reported previously. For CEMA, it required approximately 248 million traces in the time domain, with frequency domain attacks showing similar resilience. This clearly shows the immense power of DSE alone in pushing the MTD into the hundreds of millions. Huge jump.
That's already a monumental leap, from thousands of traces to hundreds of millions, requiring significantly more effort, time, and data from an attacker. But what happens when we bring in the second pillar, TVTF? How does the full Syn-STELLAR solution perform when DSE and TVTF are combined?
This is where it becomes truly unprecedented, pushing the boundaries of what was previously thought possible. With DSE TVTS AES-256, which is the full Syn-STELLAR solution, the correct key simply could not be separated out. Even after collecting a colossal 1.25 billion traces in both time and frequency domains, the attacks were entirely unsuccessful.
1 billion traces and they still couldn't get the key.
Not even close. The correlation peaks for the wrong keys were just as high as for the right key. Complete noise. This achievement of greater than 1.25 billion MTD represents a significant 25% improvement over the previous highest MTD ever reported for this type of attack against AES hardware. This is a critical aha moment because it means that with current attack methods and even the most persistent data collection, the side-channel information is rendered practically undetectable and unusable for key extraction. The combined effect of flattening the signal, DSAC, and scrambling its timing, TVTF, proves to be an impenetrable shield, at least against these correlational methods. They also performed an important statistical validation called TVLA, or test vector leakage analysis. This is another standard way to check for leakage. TVLA uses a statistical t-test, where a t-value of less than 4.5 indicates no meaningful leakage. It's a threshold for confidence. For Power SCA, Syn-STELLAR, DSMAN TVTF, increased the traces needed to cross that 4.5 threshold by approximately 290,000 times compared to unprotected AES, from just 65 traces to a staggering 19 million traces needed before you even see statistically significant leakage.
290,000 times harder to detect leakage.
Yes. And for EMSCA, it was about 70,000 times harder, from only 46 traces needed for the unprotected version to 3.3 million traces needed for the protected version to cross that threshold. These are incredibly powerful quantitative indicators of a dramatically enhanced security posture, showing that the statistical signature of leakage has been virtually eliminated for all practical purposes. The leak is just drowned out.
Those numbers are truly beyond impressive, effectively creating a black box, where before there were transparent windows for attackers. It's hard to argue with results like that. But high security often comes with significant overheads in terms of power consumption, silicon area, or performance. How does Syn-STELLAR fare in that regard, especially considering the constraints of modern chip design? You can't have a defense that makes the chip unusable.
That's a very important and practical point, absolutely. Balancing security with viability is always key for real-world adoption. You need something that works and is practical. While achieving such exceptionally high security, the overhead considerations for Syn-STELLAR are actually quite comparable, and in some cases even better, than previous circuit-level countermeasures that offered much less protection. For the DSAC-only solution, power consumption was about 33% greater, 0.2 milliwatt versus 0.15 milliwatt for unprotected AES, and the area increased by 28%, 0.19 millimeter versus 0.15 millimeter too. Manageable increases. When both DSC and TVTF are enabled, the full Syn-STELLAR solution showed about a 50% greater average power consumption, 0.227 milliwatt, and a 52% greater area, 0.238 millimeters, compared to the unprotected AES.
So about 50% extra power and area for over a billion MTD security? That sounds like a pretty good trade-off in high security scenarios.
It really is, especially when you compare it to the alternatives. And the truly significant point here, however, is its exceptional scalability. Because Syn-STELLAR is largely digital-friendly, most of its circuits can be easily designed using standard hardware description language, HDL, and then implemented through automated placement and routing, APR flows. Standard chip design tools. This is critical because it means it's readily scalable across different technology nodes, from 65 millimeters down to even smaller, more advanced nodes like 7 millimeters or 5 millimeters, significantly reducing the manual design effort and time that plagued earlier analog-heavy solutions. This pragmatism and ease of integration are what will allow this high-security solution to become widely adopted across the industry. It fits how chips are actually designed today.
So if Syn-STELLAR can provide this unprecedented level of protection with comparable overheads and excellent scalability, what are the broader implications for cybersecurity, and why does this research matter so much for all of us relying on digital systems every day?
Well, Syn-STELLAR truly marks a new era in hardware security, potentially. It sets a new benchmark in physical protection for cryptographic hardware. It makes it exponentially harder, practically impossible for now, using these methods for attackers to compromise systems through the subtle, physical side channels we've discussed. This is about establishing a fundamental, resilient layer of defense that was previously thought to be incredibly difficult to achieve in a practical, scalable way, especially with automated design tools. It's a foundational shift in how we can build trust into our hardware itself. One of its most compelling advantages, and a key reason it's so impactful, is its versatility. This is what we call a generic solution. What that means is it can be used as a simple wrapper or protective shield around any encryption engine potentially, not just AES 256. It doesn't require specific design changes for different cryptographic algorithms or their underlying implementations. You design the shield once, and you can potentially put different engines inside.
Oh, so you don't need a custom Syn-STELLAR for DS or SHA-3 or whatever new algorithm comes along.
That's the idea. This portability is huge because it allows advanced side-channel protection to be integrated much more easily and quickly into a wide range of devices and systems without requiring complete redesign of the cryptographic core itself. This dramatically lowers the barrier to entry for robust physical security, makes it much more accessible.
That makes it incredibly valuable for diverse applications then.
Yeah.
From secure data centers running complex crypto to tiny consumer electronics, and particularly for the rapidly expanding world of connected devices, the IoT.
Exactly. And consider IoT security. For the vast and growing ecosystem of Internet of Things devices, where power and area overheads are often major, critical concerns, every milliwatt matters. The DSC-only solution within Syn-STELLAR offers a highly effective, lower overhead option for robust, medium-level security. Remember, DSC alone gave hundreds of millions of MTD. It provides a strong layer of defense against many prevalent side-channel attacks without the highest resource demands of the full DSAC plus TVTF solution, making it an ideal choice for resource-constrained environments. For devices operating in potentially hostile or easily accessible environments, think smart meters, medical implants, industrial sensors, this is a potential game changer.
It seems like the digital advantage is a powerful recurring theme here, making sophisticated protections much more accessible and widespread. This truly democratizes advanced hardware security, doesn't it? Takes it out of the realm of purely specialized high-end applications.
Absolutely. That's a great way to put it. By transforming previously analog-heavy protections into digital-friendly components, Syn-STELLAR paves the way for much easier and faster integration into standard digital design flows. This effectively democratizes advanced hardware security, allowing far more chip designers to implement these robust defenses without requiring specialized analog expertise. They can use the tools they already know. They can do so with automated tools that can scale across technology nodes effortlessly. It's a significant step forward in making unhackable hardware, or at least much harder to hack hardware, a more widespread reality, embedding fundamental physical security into the very silicon of our digital world.
This has been an incredible deep dive, really peeling back the layers on a hidden threat and introducing us to a truly ingenious defense. Syn-STELLAR sounds remarkable. This research effectively makes the invisible side-channel information practically undetectable by current power and EM attack methods, pushing the boundaries of what we thought was possible in cryptographic hardware protection. It's a real testament to human ingenuity in this ever-evolving digital landscape. But it also leaves us with a provocative thought, perhaps. This research has secured us against power and electromagnetic leaks, effectively making them silent to these specific attacks. But as technology relentlessly advances, could future attackers find even subtler physical phenomena to exploit? We've moved from timing to power fluctuations to electromagnetic emissions. What new leaks might emerge from the very fabric of computing? Maybe, I don't know, thermal gradients, acoustic emissions, quantum effects in future devices, or even more obscure physical interactions that we don't yet understand or even have the tools to measure. And if they do find new leaks, will we see a complete paradigm shift in how we conceive of unhackable hardware? Or will the arms race simply continue on an even more fundamental, perhaps even atomic level? It's a question that keeps the brightest minds in hardware security constantly on their toes, I imagine, reminding us that security is not a destination but an ongoing journey, always another layer to consider.